board. I will share my iPad with you. Share. And there it is. All right, fabuloso. Okay, so on Friday, when we left off, what we were trying to do was determine the statistics of a quantum system that has discrete energy levels when we throw in a whole bunch of particles into it. All right, so again, the idea is that we have a series of discrete energy levels. So this is the energy, this is E0, E1, E2, yada, yada, yada. We throw in a bunch of particles. Okay, and so these energy levels, what these energy levels are, their actual numerical values are going to be determined by whatever the potential is of your problem. And so whether it's a quantum harmonica, whatever, it doesn't matter. All that matters is that there are discrete energy levels. Okay, then into those discrete energy levels, we throw a bunch of particles, all right? And our job is to, for each energy level, to calculate what is the average occupation number of that energy level. All right, so we want to calculate the average of N0, N1, N2, yada, yada, yada. Okay, so now, as we discussed last time, the way this problem works depends upon what kind of particles you're using. And there are fundamentally two different kinds of particles in quantum mechanics. And the first are the fermions, which are, generally speaking, these are the material particles, so things like electrons, protons, positrons, neutrons, anything you can think of that makes up matter, generally speaking, is a fermion. Okay, the distinguishing characteristic of a fermion is that it has half-integer spin. So the electron, for example, has spin a half-integer spin. Okay, now, as we talked about last time, this sets limitations on the symmetry of a multi-particle wave function. And the end result of that is that these particles obey Pauli exclusion. Okay, in other words, the allowed values of occupation numbers are either 0 or 1. So either the state has a particle in it or it doesn't. It cannot have more than one. Otherwise, your multi-particle wave function, because of symmetry, will have to vanish. In other words, it doesn't exist. All right, the other kind of particle is the bosons. And these are particles which have integer spin. Okay, these guys, again, as per our discussion on Friday, do not obey Pauli exclusion. Okay, which means that when you specify your energy level occupation values, it can be anything you could possibly dream of, all right? So you could be empty, 1 particle, 2 particles, 3 particles, yada, 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 up to infinity. Okay, so now these kinds of particles, good examples of these kinds of particles are the force carriers. So things like photons, gluons, W and Z bosons, Higgs bosons, gravitons, all the particles which carry forces are bosons. But now if you combine material particles in certain ways, they can combine in such a way that their total spin adds up to an integer. So again, something like helium-4, which is a material particle, and, you know, it's made out of protons and neutrons. It still acts like a boson because it has integer spin, because the spins of all the protons and neutrons add up to an integer value. Okay, so now where we left on Friday was we were trying to take these two kinds of particles, throw them into our quantum system with its discrete energy levels and calculate a general formula for what we expect the partition function to look like. All right, so the idea is that we take these particles, we throw them into our system, and we want to take this system and calculate the partition function. All right, now as we've discussed for a variety of reasons, the way that you want to do this is within the grand canonical ensemble. All right, and again, one reason for this is because quantum mechanics, just generally speaking, allows you to create particles out of thin air from pair production and annihilation. And so generally speaking, you can't talk about states with a specified number of particles because they're always going to be popping in and out of existence. And furthermore, it also makes the damn thing a lot easier to calculate. It just, you know, whether you believe that's a coincidence or not, that's up to your spiritual beliefs. But it turns out that, you know, when you relax the restriction that the number of particles is fixed, then you can actually calculate the damn thing inside the grand canonical ensemble. All right, so that's where we left off on Friday, was we had written down an expression for our grand partition function. All right, so we started off calculating z, which we called z grand canonical. And the way you start this is you sum over all possible numbers of particles of the grand canonical Boltzmann weight, which is minus beta E sub n minus mu n sub n. Okay, now the energy values here, okay, because our quantum system has some energy levels with specified values, the total energy of your system is just going to be those energy values times the number of particles in those energy values added over all possible energy values. So in general, our Hamiltonian was equal to, we said it was excuse me. So we had the values of our energy levels times the number operators acting on our eigenstates of our Hamiltonian, which are just the collection of the occupation numbers of each energy level. And then to get the total energy, you just simply sum over all energy levels. Okay, so in other words, the energy, that's not the way to write it. The energy of each state is just equal to the sum of the number of particles in each state times the energy of each state summed over all possible states. All right, so you take that and you stick that in there for your energy. You do a lot of algebraic massage. And what we wound up with on Friday was this expression. So the product over all alpha of the sum over all possible occupation numbers of e to the minus beta epsilon alpha minus mu times n sub alpha. All right, so now again, remember alpha here. What alpha is labeling is which energy state you're in. All right, so in other words, what you'll do is you'll start with, say, alpha equals 0. That means you're talking about the ground state. Okay, so then when you're in the ground state, you calculate the sum for the ground state. All right, then you go up to the next one, alpha equals 1, and you calculate that sum for the next energy level, alpha equals 1. So in other words, this thing in the brackets here, these are the single energy level partition functions. And then to get the total partition function, you just take those single energy level partition functions and just multiply them all together. All right, so that's essentially where we left off on Friday. So now what we're going to do is actually evaluate this damn thing. All right, so now let's do it. let's just write it down and see what we get. Okay, so first of all, we're going to do it for fermions. Okay. All right, so let's evaluate the sum. For bosons and fermions. All right, so, okay, that is getting annoying. Okay, so again, the sum that we want to evaluate is this thing inside the brackets here of our grand partition function. So in other words, what we want to do is evaluate sum over all of all appropriate occupation numbers of e to the minus beta epsilon minus mu in alpha. Okay, so that's what we're going to try to evaluate. So first of all, let's do it for fermions, because God love them, they're the easy ones. All right, so for fermions, the allowed values of N alpha, yeah, there's only 2 of them, right? Okay, so this can only be equal to either 0 or what? Hallelujah, that's the kind of problem I like. All right, so then you just plug in those values for N alpha. All right, so when you plug in N alpha equals 0, the exponent is 0. My favorite. I really need to have a talk with my family. All right, so for N alpha equals 0, we get just 1, right? Because e to the 0 is what? Then you plug in N alpha equals 1. And you get e to the minus beta epsilon minus mu. Man, it just doesn't get any easier than that. What do we got here? Yeah, that's a great idea. Where is the do not disturb? I believe that's that moon symbol there. Yes? All right, very good. Okay, so that is how you evaluate the sum for fermions. Okay, so that is our answer. So that is the single particle. So grand canonical, just one energy level partition function. Okay. Now, once you have the partition function, the next thing you want is the free energy. All right, so the free energy is just minus kBT log z. All right, so what we get is minus kBT log 1 plus e to the minus beta epsilon minus mu. Okay, so this is our single energy level partition function. This is our single energy level free energy. Again, both of these things are for fermions. All right, so write those down because we're going to need them. Okay, now let's do it for bosons. So bosons is a little bit trickier. Bosons. So for bosons, our allowed values of the occupation numbers are any integer whatsoever. Okay, so the sum is going to be a little bit trickier. All right, so again, what we want to evaluate is this. So we go from 0 to infinity of e to the minus beta epsilon minus mu n. Okay, so now when you just write this thing out, what you're going to get when you plug in n equals 0, you get again 1. When you plug in n equals 1, you get e to the minus beta epsilon minus mu. When you plug in n equals 2, you get e to the minus 2 beta epsilon minus mu. So on and so forth. All right, so now, it does not take a genius at this point to see that this is going to follow a pattern. All right, so the pattern is that we've got 1 plus x squared plus x cubed plus da 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 da, where x is equal to e to the minus beta epsilon minus mu. All right, so in other words, our sum here is equal to sum from n equals 0 to infinity of x to the n. Okay, we know how to do that. You can go look that up in your math book and see that, you know, smart people from across the spans of time have figured out what this sum is equal to. And what this sum is equal to is simply 1 over 1 minus x. Okay, so in other words, our single energy level partition function for bosons is equal to 1 over 1 minus e to the minus beta epsilon minus mu. Okay, so that is our single energy level partition function for bosons. And again, we calculate the free energy from this, okay, which is just minus kBT log of z, and we get minus kBT log 1 minus e to the minus beta epsilon minus mu. Whoops. And now, so since this thing was in the denominator up here, you get this exponent of minus 1. All right, and then because of the way logarithms work, you pull that minus 1 down in front, and so that gets rid of that minus sign. And now you are happy as a clam. All right, so this is the single energy, or excuse me, single energy level free energy for bosons. All right. Okay, so now we take those results, and now we write down the full partition function and the full free energy for our quantum system for bosons and fermions. Okay, so therefore, the partition function for bosons is this thing we just derived, 1 over 1 minus e to the minus beta epsilon alpha minus mu. Okay, and then you just multiply together all of your energy levels. Similarly, for fermions, we take this thing we derived as 1 plus e to the minus beta epsilon minus mu, or epsilon sub alpha, and then you just multiply all the energy levels. So there are our grand partition functions. That wasn't so painful, was it? No, not so bad. Okay, and to get the free energy, you just take minus kBT log of the full grand partition function. The full grand partition function is, again, a product of all your energy levels. When you take the logarithm of a product, you can write that as a sum of logarithms. Okay? So we get for our free energies that the free energy for bosons is 1 over beta sum over all alpha log 1 minus e to the minus beta epsilon minus mu. And free energy for fermions is minus 1 over beta sum over all alpha log 1 plus e to the minus beta. Probably forgot my alpha. There we go. All right, so you notice these things look remarkably similar to each other, right? They look almost exactly the same. The only difference is the sign you got in front. Okay, so for bosons, the sign in front is positive, and for fermions, it's negative. And the sign in the middle. All right, so for bosons, that's negative, and fermions is positive. All right, so in general, we can say that phi is equal to plus minus 1 over beta sum over alpha log 1 minus plus e to the minus beta epsilon alpha minus mu. Where you take the top signs, so the upper signs are for bosons, and the lower signs are for fermions. Okay, so this is our answer. Ta-da! All right, so is everybody cool now at this point? Wunderbar! So now you will recall that once you have your free energy, the way that you extract information from your free energy is by taking derivatives, all right? So what we're interested in are the average occupation numbers in alpha. All right, so now what you do is you go back and you have a look at your partition function, okay? So specifically, let's go back to right here, right here. All right, so we're looking at this thing now. All right, so you look at the general formula for your partition function, and you find in that expression the thing that you're looking for. All right, so the thing that we're looking for is the average of n alpha. Okay? And then you look and see what is multiplying in alpha. So you can see we got two choices. So we have epsilon alpha is multiplying in alpha, and we have mu is multiplying in alpha. So we could take the derivative with respect to either one of those things, either epsilon alpha or mu, and that will give us the average occupation number. All right, so let's do that. So we come back down here to our free energy, okay, and what we're going to do, just for giggles, is so we take the derivative of our single particle, not our single particle, our single energy level partition or free energy. Okay, so this is this phi alpha, that is this thing right here. So the single energy level partition functions or free energies. Okay, so to get the single energy level occupation number, so in other words the average of n sub alpha, you take the derivative of the single energy level free energy, and again you can do this with respect to either epsilon alpha or mu, and you'll get the same thing. Let's do it with respect to epsilon alpha. Okay, so this is d epsilon alpha of plus minus 1 over beta log 1 minus plus e to the minus beta epsilon alpha minus mu, like so. All right, so now all you got to do is take the derivative of this thing, which is, you know, not so bad. Okay, so when you take the derivative, you wind up getting plus minus 1 over beta. Okay, the first thing that you got to do is you got this logarithm. So when you take the derivative, you get 1 over the argument of the logarithm. All right, so you get 1 minus plus e to the minus beta epsilon alpha minus mu. 1 over that. So that's just the derivative of the logarithm. Times, okay, then you got to take the derivative of your exponent. Okay, and so when you take the derivative of your exponent, you get minus beta. Okay, and then the fact that you're taking the derivative of an exponential means it just spits the exponential back out at you. So you get this thing again, like so. So that's what you get. Okay, again, you do a little algebraic massage on this thing, so you just clean it up a little bit. You get minus plus e to the minus beta epsilon alpha minus mu over 1 minus plus e to the minus beta epsilon alpha minus mu. And then I'm just going to take my minus and plus signs out front and absorb them into my denominator down there. All right, so our final answer is the average occupation number of the alpha energy level is 1 over e to the beta epsilon alpha minus mu minus plus 1. And again, whether you choose the minus sign or whether you choose the plus sign depends on whether you're talking about bosons or you're talking about fermions. All right, so this is our average occupation number of each energy level. And so once we're done deriving everything, we're going to talk about what this thing means, all right? But for now, that's the answer. All right, and the total particle number okay, so that is average of capital N. So in principle, this is just if you take all of your average in alphas and sum them all up. But another way to get this is if you take your total free energy and you differentiate with respect to epsilon alpha, that'll give you this. Same thing. Whoops. Oh, I'm sorry. There's that minus sign should not be there. So it's e to the beta epsilon alpha minus mu minus plus 1. Okay, notice that this thing is exactly the same as this, just summed over all alpha, which makes perfect sense. All right, so is everybody good? All right, so now let's talk about what this means. Okay, so what does it mean, man? Hey, did everybody hear the double rainbow guy died? Oh, it's awful. What does it mean? All right, so let's talk explicitly about each one of these functions. So let's talk about what our answer looks like for fermions and why it looks that way, and what it looks like for bosons and why it looks that way. All right, so let's start out with fermions. All right, so we got that the average occupation number, and I'm going to put a little subscript down here, FD, for fermions was equal to this, e to the beta. It's a terrible looking beta. There we go. Epsilon alpha minus mu plus 1. So this is for fermions. Oh, I've already written that. I don't need to write it again. Okay, so this is what is referred to as the Fermi Dirac distribution function. Hence the FD subscript down there, because that stands for Fermi Dirac. Okay, so this gives the occupation, the average occupation of each energy level when you're talking about fermions. All right, for bosons, our answer is average of n sub alpha, and the subscript on here is BE. And our answer for bosons is e to the beta epsilon alpha minus mu minus 1. So it looks almost exactly the same. It's just got a minus sign instead of a plus sign. And this is what's referred to as the Bose-Einstein distribution. Okay, again, hence the BE subscript. As you can imagine, both of these things are named after the people who discovered them. So the Fermi-Dirac distribution was named after Enrico Fermi and Paul Adrien Maurice Dirac, my personal hero. And the Bose-Einstein distribution was named after, I don't remember Bose's first name, and of course, Einstein. All right, and so the Bose-Einstein distribution tells you the average occupation number of each energy level when you're dealing with bosons. All right, so that's our answers. That's what we have been after this whole time. So now let's talk about how these things behave. All right, so first of all, let's talk about the Fermi-Dirac distribution, because it makes a little bit more sense intuitively than the Bose-Einstein distribution. All right, so the Fermi-Dirac distribution is, again, e to the beta epsilon alpha minus mu over kt plus 1 in the denominator. And now, to get an intuitive sense of the way this thing behaves, let's look at its behavior for very low temperature. Okay, so let's let the temperature go to 0. Okay, so you can see if we let the temperature go to 0, that the temperature is in the denominator of our exponent. Okay, and so in other words, what's going to happen is that this. Okay, so the temperature is right here. So the exponent, which is this thing, what you're doing is you're taking the denominator of that exponent and letting it go to 0. It's getting very, very small. So in other words, the numerical value of that exponent is going to start getting bigger and bigger and bigger and bigger and bigger. Okay, so now if you look at this thing right here, so the value of our exponent depends upon two things. One is the value of the energy level that you're talking about. So that's the epsilon alpha. And the other is mu, the chemical potential.
Professor, don't you have a double beta there? Since you have the beta on the outside and then KBT is also beta?
I do, yes, you're absolutely right. Thank you for pointing that out. Oh, that scared the hell out of me. Okay, so there it is without the extra beta. All right, so thank you for pointing that out. Okay, so first of all, let's talk about some limits of this thing. All right, so if epsilon alpha is less than the chemical potential, all right, then epsilon alpha minus mu is negative. It's less than 0. Okay, so in other words, if we're talking about energy levels that are less than the chemical potential, then the exponent is negative. All right, and then as the temperature goes to 0, it becomes a very, very big negative number. Okay, and so e to the minus beta epsilon alpha minus mu goes to 0. Right? Does that make sense? Okay, so in other words, the Fermi-Dirac distribution is equal to 1 for energy less than the chemical potential, and the temperature goes to 0. All right, the other possibility is that you're talking about energy levels whose energy value is higher than the chemical potential. So if epsilon alpha is greater than mu, that means that this exponent is positive. Okay. And so as the temperature goes to 0, again, the exponent starts getting very, very big. All right, so in other words, what happens is this thing here starts getting huge, right? And so it gets much, much larger than 1, so you can essentially neglect the 1. Okay, so and this is e to the minus beta epsilon alpha minus mu over kt. Okay, and now again, as this exponent gets very, very big, this thing decays down to 0. So the Fermi-Dirac distribution is equal to 0 for energy greater than the chemical potential at t equals 0. All right. So now, what does this look like? So let's draw it. Okay, so what I'm going to draw here on the y-axis is the occupation number. Okay, and you can see that the maximum it can be equal to is 1. Which makes sense because it's fermions, right? Fermions, you can only have 1 particle per energy level. Okay, so on the y-axis is our average occupation number, and on the x-axis is the energy of our energy levels that we're talking about. Now, so what this analysis up here shows us is that there's some special value on this axis, that is the chemical potential. And energy levels below the chemical potential are fully occupied. So here, let me make this easier on myself. So the chemical potential divides the energy axis in 2. If you are below the chemical potential, the energy level is occupied. Okay? If you are above the chemical potential, it is unoccupied. Okay? So in other words, what's happening is that the chemical potential is setting the number of particles in your system, okay? And the number of particles, so, and then what happens is you just take every energy level and you just start throwing in 1 particle each, all right? So the number of energy levels you can fill up is determined by the number of particles that you can have, and the number of particles that you can have is determined by the chemical potential, okay? So you just keep filling. So again, what happens is if we draw our energy levels, and let's say that the Fermi energy, or excuse me, the chemical potential is right here. Okay, then you just start adding particles in and you fill them up from the bottom. So the first particle goes here, the second particle goes here, third one goes here, fourth one goes there. Then you're out of particles and the remainder of the states are unoccupied, they're empty. Okay, so the chemical potential sets the number of particles in your system, and that number of particles determines how many energy levels are filled. All right, so this, you know, it's an important value, and therefore you give it its own name. So mu is what's referred to as the Fermi energy of the system. All right. Okay, so now, this is what the thing looks like at 0 temperature. What does it look like for non-zero temperature? Okay, for non-zero temperature. Okay, so again, I'm just going to draw average occupation number as a function of energy. Let's do blue. Blue would make a lot more sense. So let's say the chemical potential slash Fermi energy is right here. All right, so what we just showed is that for t equals 0, this thing is a step function. It looks like this. Okay, now what happens is as you increase the temperature, the thing just starts smoothing out, essentially. All right, so now what's warmer than blue? Let's go green. All right, so for a little bit higher temperature, what happens is it still looks roughly the same, but it just starts kind of smoothing out a little bit. So instead of being a step function, it starts being smooth. So let's call that T1. And so the blue one is T0. We got T1 greater than T0. You heat it up a little bit more. Smooth that a little bit more. So this is T2 greater than T1. You get it even hotter. It's like this, T3 greater than T2. Now, if I had drawn this correctly, but because of my awful artistic skills, they would all cross the Fermi energy at the same point. And the Fermi energy is where the occupation is equal to, the average occupation is equal to a half. Okay, now the width of this thing. So essentially the region over which the thing smoothly changes. So this width of this thing over which it smoothly changes is proportional to the temperature. All right, so the larger the temperature, the wider the range over which the thing smoothly decays. If the temperature is small, then it drops really rapidly. Okay, does that make sense? All right, cool. So that's the Fermi-Dirac distribution. So the Fermi-Dirac distribution just says that there's a chemical potential which determines the number of particles in your system. You take that number of particles and you just start filling up the states with one particle in each. So below the Fermi energy, everything is full. Above the Fermi energy, everything is empty. All right, now let's talk about the Bose-Einstein distribution. All right, so the Bose-Einstein distribution, as you will recall, looks like this. 1 over e to the beta epsilon minus mu minus 1. Okay, and again, just to be super explicit, this is e to the epsilon minus mu over kt. So, all right, this thing is damn weird. All right, and it's weird enough that we're actually going to talk about this thing in its entirety for probably a couple lectures. All right. All right, so now, first of all, let's say, so it's more weird. We're going to talk about it at length, but first of all, let's look at, for low occupancy. In other words, let's look at the high energy levels. Okay, so the fact that so again, what we've got is discrete energy levels. And we're interested, so you would intuitively expect that as you throw in particles, more particles, because they're lower in energy, will congregate at the lower energy values, and fewer will show up in the higher energy levels. And so what we're interested in initially are these high energy levels, that is low occupancy. All right, so for these high energy levels, okay, we are saying we expect the average occupancy to be significantly less, to be small, to be less than 1. All right, so in other words, we expect 1 over e to the beta epsilon minus mu minus 1 to be much less than 1. Okay, and in order for that to be true, that means that this exponent has got to be really big, right? So in order for this thing to be very small, you need the denominator to be very large. Okay, so that implies that e to the beta epsilon minus mu is much, much greater than 1. Again, if that's the case, you can essentially ignore that 1. And so what you get is that the average occupation level at high energies looks like just e to the minus beta epsilon minus mu. And this looks like Boltzmann statistics. Okay, so in other words, when you look at bosons at high energy, they look just like a regular classical gas. It's only when the temperature gets low and you start looking at the occupation of these lower energy values that things start looking pretty weird. Okay, now let's make the same argument for the Fermi-Dirac distribution. So for FD statistics, we've got, so again, if we look at the high energy levels where the occupancy is going to be low, okay, and this thing is equal to 1 over e to the beta epsilon minus mu plus 1. And so again, we expect this to be very small. Same argument. For this function to be small, this exponent in the denominator must be large, okay? So we get e to the minus beta epsilon minus mu. So we get that Fermi-Dirac statistics look like this at high energy. And so again, they look like Boltzmann statistics. Okay, so both bosons and fermions at high temperature or energy, same thing, look like classical gases. It's only when you start talking about low energy that things start getting pretty freaky, all right? And so now, we did this almost exactly on time. So we're out of time. Well, there's 1 minute left. I just showed you that at high energy, high temperature, essentially the quantumness of the system doesn't matter. They just act like Boltzmann gases. It's only when you look at low temperatures that the quantum nature of the systems start becoming apparent, and they start behaving not like Boltzmann statistics. They start behaving like Fermi-Dirac or Bose-Einstein statistics. And what we're going to do on Wednesday is talk about what that looks like in detail. So specifically, we're going to talk about Bose-Einstein statistics. And I'm going to show you that at low temperatures, everything falls into the ground state. And that is what you call a Bose-Einstein condensate. All right, so on Wednesday, we're going to start talking about Bose-Einstein condensates. All right, so is everybody good? Any questions? All right, very good. Then on Wednesday, we shall resume this fascinating discussion, and we'll see how quantum gases act at low temperature. All right. Until then, my good people. Someone is F. Sad. Okay, I don't know. I hope I addressed your concerns. All right, so I'll see you guys on Wednesday.